Okay, so welcome everybody. So today we have the pleasure to have with us Haralampos Geranios from the National Kapodistrian University of Athens, who is going to talk about relating representations of the symmetric group and the general linear group.
Thank you. Thank you so much for the invitation. It's a pleasure to give a talk in the GAN seminar. So indeed, I will talk about the relations between the representations of the symmetric group and the general linear group. So let me start with some housekeeping. So my field would be an algebraically closed field. I want all the underlying geometry that I will talk about algebraic groups. So there will be some underlying geometry, and I want all this to work well. So I need algebraically closed fields. The field will have characteristic P. That's a positive characteristic. I will talk about representations. In characteristic 0, the representation theory has been sorted in the sense that we know the irreducible representations, we know the dimensions, and we know how to construct them. All together with this, we have that every representation actually decomposes uniquely into irreducible representations, so the picture is clear. On the other hand, the representation theory in characteristic P is the exact opposite. You have that you don't know the irreducible representations, and also, if I give you the same material, if I give you the same ingredients, you can build different models from the same materials, and you cannot say that I have two irreducible models and I can fit them together only one way, as you do in characteristic 0. So everything is open in characteristic P. This is where the main interest is. The best approximation, the best guess we had was probably, Lustig's conjecture that in principle would describe the irreducible representations of algebraic groups in positive characteristic. However, 10 years ago, Jordi proved that actually provided counterexamples for Lustig's conjecture. And now we know that Lustig's guess could only work for primes that they are astronomically big. So we're really back to square one in a way. I mean, that we don't have any intuition of how the irreducible representation will look like in characteristic P. Let aside what are the different models that we can actually build with these irreducible representations. I will not talk about all algebraic groups. I will talk about my personal favorite. That's the n by n invertible matrices over K. That's the general linear group. I will certainly need coordinate algebra. So that's the algebra generated by the coordinate functions and the inverse of the determinant. By coordinate functions, I mean the function that takes a matrix and gives me what is the ij position. And I really need for the coordinate algebra to work the inverse of the determinant function. Now, inside the coordinate algebra, I always have a polynomial algebra. I'm taking just the coordinate functions and I think about the algebra that they generate. These are algebraically independent. And so I have a really good polynomial algebra here. That will be the setup that I want for the GLN. Now I'm taking a G model. So I have an action of my group to the vector space. I pin down a K basis of V, V1 to Vm. By the way, all the models that you will see today, all the representations will be finite dimensional for me. Since I have an action, I can hit an element of the basis with an element of the group, and I can re-express everything in terms of the basis of V. In this way, I can create some new maps, this Rij that you see there. So what is the Rij map? It is from the group to the field K. And when I feed it with an element of the group, it tells me that you will get the coefficient of Vi when you hit the element Vj of the basis with a G. Now, if all these functions happen to be inside the coordinate algebra, this is what we call rational representations. The meaning is really natural. It arises really naturally in algebra, is the way that you create morphisms between algebraic groups. And that's the main focus in representation theory, to understand this category. When you work with GLN, you can sort of refine this. The process is that you can say that, okay, I have this big algebra, the coordinate algebra, that has all the coordinate functions generated by coordinate functions and also about the inverse of the determinant. Also, I have a subalgebra, that the subalgebra is the polynomial algebra that can see only generated by the coordinate functions. And if it happens that all the coefficients here, the coefficient functions, all the Rij are inside this polynomial algebra, then we say that we have a polynomial representation. You don't cheat at all to work with polynomial representations because given a rational representation, you can actually make it a polynomial representation. You just go and tensor many times with a determinant. The determinant is a one-dimensional model for GLN, and you can take a very big tensor product, many determinants, and make a rational representation, a polynomial representation. You can actually turn this back, start with a polynomial representation, and tensor with the inverse of the determinant, do it many times, and at some point, you will end up to the rational representations. If I understand the reducible representations for the rational reducible representations, then I know directly the polynomial irreducible representation, vice versa. So I can restrict myself in the polynomial category and talk about only polynomial representations. Since we have polynomials now, we can talk about some undergrad maths and say that I have a polynomial ring. So I have a grading. These are the vector spaces, which are polynomials of degree R. And this is beautiful because it coincides with a setup in the sense of in the representation theory. So if I give you a polynomial representation of GLN, I can decompose it into homogeneous parts. I can always decompose it in homogeneous parts, meaning that each of these parts would be a polynomial representation, and the coefficient functions, they will land in this A, K, and R now. So when we talk about irreducible models, or when we talk about indecomposable models in general, that would be homogeneous, because otherwise it would be decomposed to several parts. Do you have any questions about the setup? Cool. Just to remind you the categories. The big picture is the rational representations. I can restrict myself to polynomial representations without losing any information. And then I can go and look at the corner and say, okay, I want to know all the polynomial representations. I'm going to check only the homogeneous parts. If I understand each homogeneous part, then Bob is your uncle. I know everything. Right. Every proper talk in the symmetric group representation theory or the GLN representation theory should have one of these shapes. These are partitions. I'm sure all of you know what they are. And they are a big deal for what we'll talk about. For GLN, this is what parameterizes the irreducible representations. You have to be careful. You say that I'm taking a partition with at most n parts. I don't care at all what is the sum of these numbers. I don't care if this is a partition of R or a partition of S. I just want partitions with at most n parts. And I have a correspondence between the irreducible representations of GLN and these partitions with at most n parts. That works in complete generality. The field is independent here. The problem is that if you add the extra that the field is of characteristic 0, you have exactly this picture, but you can also say that, and I can actually construct these models. When you're characteristic P, this is the most general thing that you can say, that I know how to label these models, but I don't know anything about it. I don't know what dimension, I don't know how to find the proper basis. I don't know anything. Now, if you want to check about homogeneous stuff and you are really interested about taking only a corner where the partition, the lambda i's add up to R, then okay, you will have a correspondence between the reducible representations of GLN of degree R with all the partitions that they add up to R. That's all that concerns the reducible representations. We're going to some much more friendly model. That would be the induced model. Now, I just included the main definition, but I will construct it at some point. I'm taking a partition which has at most n parts. And I'm not thinking about GLN. I restrict myself to a Borel subgroup. Now, Borel subgroups, they are all conjugate. I can pick my favorite one for GLN. The best one to pick in this situation or to induce, it would be the lower triangular matrices. And when you pick all the reducible representations for Borel subgroups are one-dimensional. So brief history is that when you have the torus, how you debone an algebraic group, you start with a torus, a maximal tori, and let's take here the diagonal matrices. Here, if you think about the diagonal matrices, the one-dimensional representations correspond to weights, and every representation of the diagonal matrices decomposes to one-dimensional stuff that they will be with multiplicities, but everything will decompose. Now, you can sort of inflate this action of diagonal matrices to the Borel, meaning that I'm thinking about diagonal matrices, then I want to put the extra chunk and make a lower triangular matrix. Now, I will think about the unipotent part that doesn't do anything to the representation, sort of cheating, and say that the actual lower triangle matrix will act like the diagonal matrix, but it works, actually gives you um, the full set of irreducible representations of the lower triangular matrices. It will be the same without the diagonal matrices. What you're losing, you must lose something. There is a price to pay. You lose that you don't have the decomposability. Here, when you go to even to the Borel subgroups, models start not decomposing in characteristic P. However, I know now for a partition lambda that I can associate a one-dimensional representation for the lower triangle matrices. And from there, now I'm properly induced with an induced functor to GLN. And this is how you construct the induced model. What do I know about it? It offers shelter for the irreducible representation. So for any partition lambda, you will find the irreducible representation living inside the induced model. In fact, you have something stronger than that. You have that this is the unique irreducible model that lives inside the induced model. The way to say it mathematically is that the induced model has simple SOCL. It means that you will find only an irreducible representation, and you can actually say that the labeling matches up. Then the natural question is, and what else? What else can you find on top of this model, on top of the irreducible? In other words, with using terminology, it means what are the other composition factors and how many times do they appear? So you talk about the decomposition numbers. The answer is, of course, that we don't know. In fact, it's even worse because this problem about knowing the composition factors and exactly how many times they do appear in the structure of the induced model is equivalent to know the irreducible representations. So this is, if somebody one can set this problem in this way, can say that one of the biggest and the major problem in representation theory is to solve the decomposition number problem. When they refer to the decomposition number problem, they actually mean to know the characters. These problems are equivalent. We know really well, as I said, the induced models. Actually, as vector spaces, the structure is characteristic free. So the basis that you'll find over any field would be the same. We can describe the basis, we can describe the characters. What changes is that in characteristic 0, the induced model is actually the irreducible representation. You will not find anything above. But in characteristic P, then it starts having other composition factors above, and you don't know about them. Some classic induced models is when you take the partition to be just one, the partition that has only one. That is the model of column vectors, meaning that you take just a column with n positions and you multiply with GLN from the left. This is your representation, and it's associated. It's an induced model, and it's associated to partition one. If you take many times one, then you have the Rth exterior power of the natural model. And if you take just the partition, the other extreme, that you take R, just a big number, then you get the symmetric power of the natural model. And as I said, you can construct all of them. There are many ways to construct them. Green has a beautiful way with bideterminants. Akin, Buxbaum, and Wayman have a very nice way using the whole algebra structure of the exterior algebra. We will see actually this way in a minute. It's a very nice game to play and see how you can actually translate the induced model. However, in my opinion, you're using homological tools and kind of give you some freedom is to actually say that it is really an induced model, because you can do things like I'm in a Borel and I'm inducing back to GLN. I have homomorphism. I might restrict back to Borel and see and get results from there. Right. Let's construct it. It's a game that we have to play many times today, and the construction is we have some fun. So I take a partition. Unfortunately, when you want to go with this construction, you have to consider the transpose of this partition. The transpose is that you flip your partition, and now your columns become rows, and the rows become columns. You rotate the bit. It is the same technique in order to construct the induced model. It is the same technique to construct tilting models. They will not appear in this talk, but they are a big deal today for the representation theory, because they might be the new way out in order to understand the reducible representation C characteristic P, according to all the recent work of Jordi. So what are you doing? You take this transpose partition and you associate for each part an exterior power of the natural model. So you take this big tensor product in front of you. And what you want to do is to choose two consecutive pairs. Take I and I plus 1, and I can run from 1 to L minus 1. But taking the consecutive, it doesn't matter. You can do it with any pair, but it gives you some freedom that you can actually concentrate their neighbors. Isolate it and think about exterior powers that they will be higher up on the left, but you will decrease on the right, whatever you took on the left. So an example would be that instead of thinking the lambda I prime and on the right the lambda I plus 1 prime, I think on the left lambda I and I add something and I add 1, but I have to take it to decrease it from the right hand side. Because I'm in a Hopf algebra situation, so exterior powers form the grading of the exterior algebra, and the exterior algebra is a Hopf algebra. So I can split, which means other people call this diagonalization. And I can go from this wedge plus 1 that I have, go down to the lambda I prime wedge, tensor with E. And then, because I have a multiplication, it's a Hopf algebra, I can merge. So what is the gain? I increase a little bit the left-hand side, decrease at the same time the right-hand side. I want to keep the degree the same. Split on the left, merge on the right. When you do this, you're actually focusing on the consecutive pair that you chose. However, you can see that this is a map coming from all these tensors where I leave all the other tensors alone, meaning that I just put some extra tensors with the identity. I'm only touching this consecutive pair, and then all the other tensors will go down with the identities. You don't do it only once. Let's do it again. I can increase by 2 the left-hand side, decrease by 2 the right-hand side, split because I have a Hopf algebra, merge. And I'm back to the target. Keep going, do it many times, do it as many times as you can. The last time that you can do it is take everything on the left, nothing on the right, just a zero, which is the zero of your exterior part here, just your field, split, merge. Okay, now, as I said, this forms maps that if you think also that I'm doing this only to the consecutive pair and I leave all the other bit alone, meaning that I'm just putting identities, they form maps that everything will land in this fellow that we have here, in the big one. If I take the sum of all these maps and the sum of over all the possible ways I can do it, and the sum of all the consecutive parts that I have, all the consecutive pairs that I have, I form a very big image inside my tensor product of exterior powers. People refer to this as Buchsbaum's box map. The reason is I think that the symbol appeared only the first time in the Akin, Buchsbaum, and Weyman paper. And if I take the quotient, that is my induced model. It is sort of magic. It works really nice. It is an analog of what happens inside for the symmetric groups and the spectrum modes when you have Garnier relations. We will go to this, but it gives you a very concrete construction of the induced model, which is one of many, as I said. Biomodels. Right. Now, I want to build a dual to the induced model. It would be a bit stupid to take the normal dual. So if you think about a polynomial representation, one of them is the determinant itself. It's a very nice representation. And if you think about it, it's a polynomial withCij's. So it is a polynomial representation. However, if I'm going to take the normal dual, the dual that you take normally, that would be the inverse of the determinant, and I'm out. I'm out of the polynomial category. So there is a remedy for this. You take the dual as a vector space, and normally when you take the dual of a model, then the action that you have is that you act with a G inverse on outside of your map. The remedy here is to forget the inverse and put the transpose. That will give you a model. It will make the dual vector space a G. It will give it a G model structure. It will have all the nice properties that you want, and it will land in the polynomial category again. So the Weyl model for us, it is the contravariant dual. This is the name that we associate to this form of duality. Okay. So induced models, we're offering shelter to the irreducible representations. Here, the Weyl models, they do offer shelter, but they're a bit, they put them in the roof. They put them in the attic. So there is an irreducible representation, and you can find it in the head of this model. What I mean with the head, I mean, you take the radical of this model, and you cut it out, and you'll find only one, a unique irreducible representation on the top. And that could be the same labeling, it's the lambda. So this gives you a different way to recognize the irreducible representation, now not inside, but on the top of this model. Of course, you would expect that because there is some duality here. The question is, what else is going on? What do you have here? Same old, same old. We don't know. In characteristic zero, we do know. Weyl models and induced models coincide, are both the irreducible models lambda. In characteristic P, we don't know. It is exactly an equivalent question. If we knew the decomposition numbers and if we knew the composition factors of the Weyl model, we would know the composition factors of the induced model, and in turn, we would know the characters of the irreducible models. So it's a no-go area. It's a little bit, it's really difficult, and sort of we don't have an intuition of what's going on there. Some Weyl models that we know, if you take again the partition one, that would be the natural model of column vectors. It is subdual. and it is the same. Nabla 1 and delta 1 coincide here. In fact, this tells you directly also, you could have proved it directly, but this tells you that E is an irreducible representation. Same holds for all the exterior powers. They coincide here, and they give you an irreducible representation. So while and induced molded don't see the difference. When you go to the partition R, you start. It's the first time that you'll see an easy example that you'll see some difference, right? You'll see something different. Beforehand, we had that the nabla of R is the arc symmetric power of the natural model. Here, the delta of R, it is the arc divided power of this model, where, and makes total sense, the divided power is the dual of the symmetric power and vice versa. I want to construct them. Again, I will go Buchsbaum style. I thought that I heard Michali's voice at some point, and if he's around, yeah, Buxbaum is the supervisor of Michalis. So I'm taking a partition which has at most 10 parts. This time I don't think exterior powers. I think tensor products of divided powers. I again isolate a consecutive pair here, and I will play the same game. Divided power algebra is a Hopf algebra. So I have splitting and merging. I have this factory available so I can use it. First, I have to do the same thing. Think about going a little bit higher up on the left, go lower down on the right. So let's do then example +1, split, merge, and you are exactly where you want to be. Think about starting from here, split, merge, and you're exactly where you want to be. Keep going, reach the end where you will find everything to be put on the left, nothing on the right, meaning that you just left with a field. Split, merge, and you're on the target. Do this for all the possible cases you can do it. Do it for every consecutive pair. Take the sum of all these maps that you created. When you pick, as I said before, when you pick your favorite pair, imagine that everything else stays stable with identity maps. Create a big map, and then take the image of this map, and here's your data model. The data model will be a quotient. Again, this time a quotient of the tensor product of these divided powers. Beforehand, we had that the induced model would be a quotient of the exterior powers. That was all about GLN, and I think it will be a good place to ask if there are any questions. I cannot see, by the way, things. Julio means I can move on. Right. Now, the other group that I want to put in the mix is the symmetric group. Again, partitions. For GLN, the partitions were sort of, they had some bound, and the bound that can have at most n parts. N is the rank of my group of GLN, and that was the connection with GLN. Here, the symmetric group is the symmetric group of on R elements. And actually, this time, I do really care of what the parts of the partition, where do they adapt. I want them to adapt to R. I don't care about the length. They can be whatever they like, the length. But I do want to adapt to R. Oops. Now, if you have seen any character theory course, you know that partitions parameterize the contiguous classes of the symmetric group, and you know then that actually correspond to irreducible representations of characteristic 0. This is not happening in characteristic P. I will make some point that whatever you heard for GLN and characteristic 0 is exactly the same is true for symmetric group and characteristic 0, that we know how to label the reducibles. We can construct them. They call the spect models. We will see them in a minute. We know everything about them. There is only one problem that always comes in mind when I say we know everything about them in characteristic 0. It is the Kronecker coefficient problem that says take two spect models, two irreducible representations of the symmetric group, tensor them together. Tell me, since I can split everything to irreducible representations again, I can decompose it. Tell me what are the summands. Tell me what are the decomposable, what is the decomposition. This is hardcore, really open, nobody knows. And the only work that I'm aware of that has made some promise is the work of De Visser and Bowman. So this is, but as a picture, we know really well what is the representation theory of the symmetric group and characteristic theory. Here, these are the irreducibles, and you know from Maske's theorem that everything decomposes to the irreducibles. So again, the picture is clear. Let's go to characteristic P. First of all, I don't need all the partitions of R. I need the restricted partitions of R. And by P-restricted partitions, I mean that the difference between the rows are less than P, and the last row should be also less than P. And I have a correspondence. I have that for any P-restricted partition, I can give you an irreducible representation, and that's all actually. This is how can I construct all the irreducible representations. By the way, construct, I didn't really mean it. I don't construct them, I just label them. What are they? Nobody knows. In fact, by some work of Erdmann, if you knew the irreducible representations of GLN, there is a hacky way that you can get directly the irreducible representations of the symmetric group. If you know the irreducible representation of the symmetric group, it's not immediate, but yes, again, you will know the irreducible representations of GLN too. But you have to put some extra thought on this. The point is, once again, we're on the same problem. This problem is equivalent to knowing the irreducible representation of GLN, which is know the structure of the induced models, which is know the structure of the Weil models, etc., etc., etc. Right. However, we said for induced models and irreducible representation of GLN that they offer shelter. We said that we don't know how the irreducible models look like. However, we can find places that we can recognize them and start working inside there. Or if you want to work with the Weil model, work on the top of the Weil model. It's a good idea to find a place where these irreducible representations of the symmetric group live. So if I take a partition, I can always associate to this the spect model. The spect model, as I said, is a reducible representation of the symmetric group in characteristic 0. It lives also in characteristic P, how it has the same basis, however, it has a different structure, and it's not irreducible in general anymore. If I take a P-restricted partition, then I can tell you sort of the same picture, and you can see the analogy here. You'll have that the reducible representation lives inside it. By the way, I'm following Green's notation in this talk, meaning that I labeled my irreducible representation of the symmetric group with P-restricted partitions and not with P-regular that James does. So for the spect model, my irreducible representation, the P-restricted one, lives inside it. If you open James, who is the mastermind in representation theory of the symmetric groups book, he will tell you that it lives actually in the head of this model, but he thinks about a different labeling. So I think about P-restricted, which is Green's notation, and James thinks about P-regular, which is James' notation. They were friends, these two, so they knew what they were doing. If you want to know what else is there, same old, same old. We don't know what is the structure of the spec model. If we knew, etc., 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 the story that I said many times, we would know everything. Some spec models that we love and like is I'm taking the partition just a big fat R, just one thing, and that's going to be the trivial model. And I take the thinner version of these that I'm going to take 1, 1, 1, 1, 1 R times, and that's going to be the sign representation. Again, you can construct and you can write down every spec model you like. There are bases available, and you can see what is going on. So, recap, it was that for the induced models, I was able to sort of write the picture, meaning that we don't know anything. It's just a simple model and a question mark. Weil models, the same. Spect models, the same. The next step for the GLN version was to actually find a nice place where I can find the induced model and describe it as a quotient. I found a nice place to construct the Weyl model I described as a quotient, and now we'll do the same for the spect model. So unfortunately, I have to consider again the transpose partition in order to do this construction, and I'm going to take the sign permutation model. I didn't include a lot of details about this, but I will tell you briefly what it is. So I'm taking my symmetric group, and I take the partition lambda prime. I can associate to this lambda prime a parabolic subgroup. More people call it's very well known as the Young subgroup. It is direct product of smaller symmetric groups, and I'm taking the sign representation of the Young subgroup associated to lambda prime, and I'm inducing to the big symmetric group. This is inducing in the usual way that we do in finite group theory, and that's the sign permutation model. If you run a little bit this idea, it gives you that actually the spect model is a quotient of the sign permutation model. And it's not really hard to prove this. If I stick with my partition and consider a different and easier model now, it is that I'm not going to take the sign. I'm going to take the trivial model. I'm going to take the associated parabolic to partition lambda, the Young subgroup that's associated to lambda, if you like. And I'm inducing the trivial model from S lambda to my full group, then I'm gonna take the one and only permutation model, so corresponding to lambda. And the permutation model is something that we really like, we can understand, and actually give us a home for the dual of the spect model. So the dual of the spect model would be a quotient of the permutation model. Coolio. So I think that this is all I needed to set up for the symmetric groups. And yes, and now I can put things together. So Polen are, for me, it is the category of polynomial representations of GLN of degree R. So I'm thinking only of a corner of homogeneous representations of degree R. And I have a functor that says that I can actually relate this category with the models of the symmetric group. The way to see it is really easy if you think in terms of algebraic groups. There is an alternative way. I will describe it in a bit because I know, for instance, that Makis loves idempotence in algebras. You take a polynomial representation of GLN of degree R, and you think about it as a T model again. I am meaning that you just think about diagonal matrices, act on this, it is a GLN model, so it is a T model, but all T models decompose to one-dimensional models. We know that they are associated to weights. Take the weight that is 1, 1, 1, 1, 1, put all this space together, take the weight space, that is all the vectors that they have this property, and that will be a model for the symmetric group. And that's how you define the Schur functor. Examples. So not examples, actually. That's not correct. Results, and that's all due to Steve Donkin and Green. Mostly is that when you apply the Schur functor in the tensor product of exterior powers, then you get the sign permutation model. So you can relate, the first relation that you see of all the models that you have seen in the picture so far is that I'm taking tensor product of exterior powers, apply the Schur functor, I take the sign permutation model. I take tensor product of divided powers, this comes next to the least because this is how I constructed the Weyl model. I take the Schur functor and I take the permutation model. I take tensor product of symmetric powers. They haven't come yet into the picture, but they will come soon when I finally talk about the problem that I want to talk about. I take the Schur functor on this thing, and I take again the permutation model. So that's an indication that things will start go wild, because two different things in GLN, the Schur functor recognize them as the same thing inside the symmetric group. The divided powers, the tensor product of them, it's a projective model. The symmetric powers, the tensor product of them, is an injective model. they are actually dual to each other. They're not the same. However, when you apply the Schur functor becomes a little bit dummy and doesn't understand. Say that I will give you back the permutation model anyway. When you apply the Schur functor on the induced model, you take the spect model. So now everything makes sense. Why all these problems, they are so strongly related. Why all these pictures that you're seeing with the question marks actually are sort of like the same picture, that I know something and I don't know anything else. When I apply to the val model, I take the dual of the spect model. And when I apply the Schur functor on the irreducible model for lambda restricted, P restricted, I will take the irreducible model. Of course, for the GLN, I didn't have to take lambda to be P restricted. It is, if I take it, I will get what I want, which is a reducible representation of the symmetric group. If you take any, then not be restricted, then you'll get a zero. So it's easy going. We understand the Schur functor really, really well in this context on the basic models of the representation theory that we're dealing with. Now, as I said, all this is Steve's results, and green, I did nothing to do with me. It was way before I come to the picture. But then you have the inverse, the right inverse functor of the Schur functor. It was defined by Green in his masterpiece, the polynomial representation of GLN. What it does, take a model for the symmetric group. You can see the symmetric group acting on the left. Now, the symmetric group also is tickling the R-fold tensor product of the natural model, just permutes on the right. So I can put them together, I can bond them together with a tensor product, and now I have all the flexibility to act on the left with GLN and create actually a GLN model. Okay, now this is an inverse of the Schur functor, meaning that it's only the right inverse. If you apply this guy and then you apply afterwards the Schur functor, you'll get what you started with, but not the other way around. And that's a problem. If actually we could understand what was going on, we could have solved a lot of big problems with representation theory. I will elaborate a bit about this in a bit. So this is where I come in the picture, and most of all these results, I don't want to go step by step who did what, appear in joint works with Steve Donkin or personal works or Steve's personal works. So if I apply the G functor on the sign permutation model, I will get the tensor product of the exterior powers if the characteristic is not 2. So for P is odd, then actually we have a full inverse. Things will go back to where you started, but for P greater or equal to 3. If you take P to be 2, then bang. The G of the sign permutation model would be the tensor product of symmetric powers. Now, what happened here is that I started with exterior powers in GLN. I actually put the Schur functor and then gave me the sign permutation model. But when I went to the sign permutation model and applied G to go back, I got symmetric powers. I didn't get back my exterior powers. If you can see what is the problem, what confuses here the G functor and the Schur functor is this sign. That if you're in characteristic 2, yes, fine, you can separate symmetric powers and exterior powers, all right, because their difference is not only the sign, they have other differences too. But on the right, there is no sign anyway, you're in characteristic 2. And that was the only difference that the Schur functor could see beforehand. So you will get the symmetric powers here, and that's a problem. But we know what it is. When you take G on the permutation model, hunky-dory, you'll get tensor product of symmetric powers. Nothing is changing. This is independent of the characteristic. Now, if you take G of the spect model, that's the induced model again when P is different than 2. So I prove for this for P greater or equal to 5. First appear in a paper of Nakano and Hemmer. Then Steve Donkey had a different proof that, again, for p greater or equal to 5. And then myself and my PhD student, Adam Higgins, we find an independent proof that also covered the case with p equals 3. That says that for p odd is always true, you'll have a full inverse and everything's great. So this leaves, we wanted to complete this and say that, okay, so what? So what's going on in characteristic 2? Open. And open and really, really difficult problem. It seems like a characteristic 2 problem, but it's not. If you think about in any characteristic, what is the inverse of the Schur functor on the dual spect model, this is open in any characteristic, in any positive characteristic. And I will give you a description and I will tell you what's going on, but it was open in any characteristic. And actually, finding the right inverse of the spect model in characteristic 2 is a sub-problem of this last one. The reason for this is that the dual of the spect model in characteristic 2 is again spect model. It's not the same spect model, but it's again spect model. So if you knew what is the G of the spect model dual in any characteristic, you would know what is the G of the spect lambda in characteristic 2 for free. Cool. So what do we have? All right, alternative description. I thought that that would be good for people that they like to work with algebras instead of algebraic groups. All this setup can be done in the language of algebras. Again, this is in Green's masterpiece. He said that I'm going to think about, I told you that A, K, and R are this vector space, these homogeneous polynomials onCij's of degree R. This is the coalgebra. I'm going to take the dual. The dual of the coalgebra is an algebra. And this is a Schur algebra. It's a very well-known algebra in representation theory. The polynomial representations of GLN of degree R, the category, is equivalent to the modules over the Schur algebra. So we can just ignore the polynomial representations of GLN of degree R and work with S modules, if we like. If I find there is a suitable idempotent that if I hit the Schur algebra on the left and on the right, I'm going to take the group algebra of the symmetric group. And then I can translate also my functors. And I'm going to say that I'm going to take a model V. And what is the Schur functor that beforehand was the weight space? Now I'm going to say that just here with this idempotent on the left, you have an ESC model. And this is exactly the same picture you had. I can also do the right inverse. It is that I start with ESC mode, meaning representations from this algebra ESC, which for this suitable idempotent, it's actually the group algebra of the symmetric group. I'm taking a W and I say that you are a left ESC model, but SE is a right ESC model. I can put you together nicely and now I have the freedom to act on the left with the S. So that is the algebra description of the setup here. Of course, for this, you don't need to find this suitable idempotent in order to do this picture about the Schur functor and the right inverse. It works for every idempotent that you want. However, you need to find the suitable idempotent in order to make the identification with the group algebra of the symmetric group. Cool. So we move on. Reminder, because we had this break about what is the how can I see things through algebras. Induced model, it is a quotient of tensor products of exterior powers. Val model, it is a quotient of tensor products of divided powers. This guy, the one that is actually open in any characteristic, here is a description. It is the quotient of the tensor product of symmetric powers, which is very nice because actually tells me that all these things works categorically, right? I mean, I have the same picture, and I will tell you what's the same picture. I have the same strategy. I have the same factory, the same arsenal here, and I can put exterior powers. I will find induced model. I'll put divided powers. I will find the Weil model. I can put symmetric powers, and now here you go. This is the model that forms. It is the right inverse of the GeoSpec model. And when I say I have the same factory, you will get this map that is box hat. So Bookstrom has the box map. He also used the notation of bar box for the Weil model. I had to put a hat there for the new map, but it's the same map categorically. Isolate to position. You can take consecutive pairs. You can take any pair you like. Go higher up on the left, decrease at the same time the right-hand side. You have, again, a structure of a Hopf algebra, so you can split and merge. Do it for all the possible choices. Do it for every consecutive pair. Take the sum of this map, take the image of this big map, and then cut it from the tensor product of the symmetric powers. And here you go. That's the description. Right. So this is great. However, it is a bit not really friendly, meaning that if I replace exterior powers there, I have the induced model that is actually an indecomposable model. If I put divided powers, that is also an indecomposable model. It's a Weil model. This can really decompose. This can be big, 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 big. I know now that what is the dimension of this thing. I can say a lot of things about discussion. However, to say that you know the form and everything, it sounds really difficult to me, but it's something that I want to finish sooner rather than later. I will tell you how big it can be through an example, but I need some more terminology to do this. Before I do this, I will tell you this connection again, that knowing now the general picture for the GeoSpect model in characteristic to the GeoSpect model is a spect model again. You have to, though, change your partition, the labeling, and put a transpose. And so you also have a picture of the GeoSpect model in characteristic 2. Cool. Right. Where should I go now? Now, probably I should also mention that something that's another big problem, that in characteristic 2, spect models are a little bit weird. In any other characteristic, they are indecomposable models. So they're in characteristic 0, they're irreducible. Then you move on to positive characteristic. You say that, okay, they are not irreducible, but in odd characteristic, they're indecomposable. James proved that. In characteristic 2, though, they are really, really decomposed sometimes. And the first example was given by James, and it was in the 1970s. Then sporadic examples by Murphy, Fagers, Dodge, and then Steve and I, we actually created infinitely many families of decomposable spect models. And the cool thing about our description was that we actually described the decompositions. We said that there are in the other papers, they were just finding direct summand. And for us, we really, really described the full decomposition of the spect models. So how I came into this problem of finding the G of the GeoSpect model actually started the other way around, started from here. I wanted to know exactly to solve the problem of characterizing all the decomposable and decomposable spect models in characteristic 2. I then realized that actually this is if and only if I turn everything in GLN, because this is what I do for a living. I take problems and I want all the time to translate in algebraic groups. I don't want to work with a symmetric group directly. Then I realized that we don't know this, so I have to find a structure. But then I realized that it belongs to a much bigger problem, that is the G of the GeoSpect model. And then this is all the story, how everything came together. So in order to give you a glimpse of how weird this can be and how difficult, and the structure that be much more complicated, I need to talk a little bit about injective models. Again, mirror pictures, GLN symmetric group. So take a partition, take the associated tensor product of symmetric powers, This is an injective model. Actually, it's not necessarily an decomposable injective model. It decomposes, and it decomposes to in this way. They will have a formula. Now, the I lambda is a decomposable injective model corresponding to partition lambda. And there are going to be other indecomposable injective models. If you really wanted to know what are these, how many times do they appear, unravel it back and you'll find out that actually this leads to the knowing what are the characters of the irreducible representations. So, but this problem here is exactly will take you back to the same problem. So you have to know the characters of the irreducible representations. However, we know that for any partition, there exist decomposable injective models, and we call them I lambda, and they appear, you can find them as direct summands of tensor product of symmetric powers. The mirror picture for the symmetric group is that I start with a partition of R. I'm thinking about my permutation model. I think that this decomposes to indecomposable summands. They have a name. They called Young models. Again, if you want to know how many times and what Young models appear in this picture, it is the same about knowing what is the composition of the symmetric powers, which is the same about knowing what are the characters of the irreducible representations. So again, we have a formula. Can we really say something about this? Not much. And for any partition of R, we have a correspondence between partitions of R and indecomposable summands of permutation models. I could just write there correspondence between partitions of R and Young models, indecomposable Young models. Cool. So F and G on these two new objects, if I'm then going to take a partition with at most n parts of R, I have my Schur functor. I give you the injective model. It returns the Young model that was known again by Steve somewhere in the 90s. And then Steve and I proved that actually it works beautifully the other way around. I give you the Young model, and you get back with the inverse functor, the injective model. So here you have, again, full inverses when we talk about these specific models, right? Cool. Take now a spec model that corresponds to a hook. You don't have to go really far in order to see how weird this will become now. This is one of the models that this one of the decompositions. It's just an example of the families that we have in this paper with Steve about decompositions of spec models into many things. We're in characteristic 2. So taking G on the spec model, it is the same by taking G on the dual of spec model. And here it is. It will be a direct sum of many injective models. So it points out that although you have the picture of now how G spec lambda looks like, and I know the base and I know the dimension, it will actually be really hardcore to say what is the structure, how I can visualize this model, because even for the models that behave nicely, and this is a nice case, because I can put my hands on and say that I know the spec model is Young model. We have proved that Young models go back to injective models, and now here you go, put it all together. This is the model. This is not happening all the time. So spec models will not be necessarily in characteristic to direct sums of when they decompose. Sometimes they don't decompose, but when they decompose, they would be direct sums of weird stuff. And sometimes will be a summand can be then an irreducible representation, and then you will need to say what is the G of this weird stuff, and this is difficult. In fact, nobody knows what is the G of the irreducible models. If I put irreducible models, I cannot tell you what is the G of the for the symmetric group. I cannot tell you what is the G of this when I take it back to the GLN. If one knew this, for instance, it would get Fletcher-Martin's conjecture about the self-extensions of irreducible models for free. If one knew the structure, because you will translate the problem, one will translate the problem in GLN, and then it will be fine. But you don't know where to start with because you don't know how to drag back to GLN. And what's the time? It's 35. I passed my hour. So yeah, thank you.